Welcome back to the deep dive. So if you've spent any time at all working with source code, you know that basic rhythm of Git. You commit, you push.
Maybe fight a merge conflict here and there.
Right, exactly. And that's the stuff that, gets your code stored and shared. But here's what I think is the critical gap. In the modern world, the real work doesn't even start until after that push.
That's so true. You can be a master of every single Git command, but if you don't get the machinery that takes your code, runs the tests, builds it, and actually gets it out the door, you're sort of just handing over a manuscript and hoping for the best.
That engine room is exactly where we're going today. We are pulling back the curtain on a really critical component that powers all of CI/CD.
Yeah.
The GitLab Runner.
Yeah.
This deep dive is all about solidifying your foundational understanding. So you can go from just being a developer who pushes code to an engineer who actually successfully delivers it.
And our mission here is really to decode the runner. We're going to talk about how work is managed versus executed, the surprising security stuff around how they communicate, and the difference between using generic machines versus highly specialized ones.
And this is often the difference between a pipeline that just works and one that is constantly failing for weird reasons.
Exactly. Flaky errors often live here.
Okay, so let's unpack this core architecture.
Yeah.
When I was starting out with CI/CD, I really just pictured it as one big magic system. I'd push my code, and GitLab just did things.
Right. It feels like magic.
But you're telling us it's much more decentralized than that.
It is absolutely decentralized. And, getting this separation is probably the single most important step to debugging your pipeline. You've got two completely distinct things at play here.
Okay, so let's start with the one most people know.
That would be the GitLab instance. Just think of this as the central manager, the brain. It's the website, the UI you log into, the API, the database where your code lives.
And where the .gitlab-ci.aml file is.
Exactly. Its job is pure coordination. It holds the clipboard, it checks the rules, and it knows what needs to be done. It has the to-do list.
So the manager with the schedule and the rules of the road.
Precisely. Now we bring in the second piece, the GitLab Runner. This is the worker, the muscle. And the runner is a totally separate application that you install on some other machine.
Like a server, a laptop.
Could be a server, a VM, a cloud instance, anything. And its only job is to connect to the manager, grab a job description, and then run the actual script commands.
So the first big takeaway for anyone listening is that GitLab coordinates, the runner executes, the manager plans the worker actually does the work.
And they are separate pieces of infrastructure.
Right.
Understanding that separation immediately sets you up for the next concept, which this one often surprises people, the communication flow.
Okay, because the intuitive model is that the manager pushes the work out. It sees the code push and just says, hey, runner X, run this job.
That's what everyone assumes. But think about the network nightmare that would create. The manager would have to know how to reach every runner. Every runner might need a public IP. The technical reality is generally the opposite, and it's actually a huge security feature. The flow is mostly a polling mechanism.
A polling mechanism.
Yeah.
So the worker is the one starting the conversation.
Yes. The runner is the proactive one. It's
right.
Constantly reaching out to the GitLab instance over a secure connection, and it's just asking over and over and over, got any work for me? Got any work for me?
It pulls the job in.
It pulls the job in. That's why we call it a pull-based architecture.
That totally flips the dynamic, but I can already see why that's a big deal. Why is that pull method so valuable in like a big company?
Well, the main things are security and just network simplicity.
Mm-hmm.
Imagine you have a runner installed deep inside a really secure private network.
Okay.
Maybe a machine that needs to talk to a sensitive internal database. If GitLab had to push the job, you'd have to poke a hole in your firewall to let it in.
Which is a security nightmare. Nobody wants to do that.
Exactly. But because the runner is the one reaching out, it only needs outbound internet access. You don't need any incoming ports open. It just massively simplifies your firewall rules and lets you run these things in very isolated, secure places.
Wow. So the worker proactively looking for tasks just solves a huge network headache before it even starts.
It's a really powerful model. And once we get that communication flow, we can talk about how they're configured because not all runners are created equal. You've got this core difference between shared and specific runners.
All right, let's define those.
Shared runners are pretty much what they sound like. They're available to everyone, to all the projects in a GitLab instance. If you're using GitLab.com, these are the free ones they provide.
They're convenient, generic.
Totally. They're the default, the utility knife of CI/CD. Then you have specific runners. These are runners that you register and you tie them to one specific project or maybe a specific group of projects. They are your infrastructure that you manage yourself.
Okay, so this is where I'd push back a bit. If the shared runners are free and easy, why on earth would anyone go through the hassle and the cost of setting up their own specific runner?
That's the million-dollar question. And the answer is always control and unique requirements. Shared runners are great for, a standard Linux build, but what if you need to compile code for a special ARM chip? Or what if you need a really high-end GPU for machine learning?
Things you won't find on the shared fleet.
Exactly. Or what if you have to build on a very specific older version of Windows or Mac OS, or you have some proprietary software with a license server that's only available inside your company network?
I see. So shared is kind of like taking an Uber. It's easy, gets you most places.
Right.
But if you have to haul, I don't know, specialized heavy equipment, you have to buy your own specialized work truck. That's the specific runner.
That analogy is perfect. It captures the trade-off exactly. The specific runner is more work for you, but it gives you total customization.
And there's a money aspect too,
Yeah,
right?
yeah.
Especially in GitLab.com.
Oh, absolutely crucial detail. Shared runners use up your CI/CD quota minutes on your account. If you build a lot, you can burn through that fast.
But a specific runner.
Because you're paying for the server it runs on, the minutes you use on that runner generally do not count against your GitLab quota. For high-volume teams, that can be a huge cost savings.
Okay, so control, customization, and cost savings. That makes a pretty compelling case.
It really does. But, now this creates a new problem, a routing problem.
How so?
Well, if I have 5 generic Linux runners, 2 specific Windows runners, and 1 with a GPU, how does the manager know where to send a job? It can't just send a Windows job to a Linux box.
Right. You need a matchmaking service.
That's exactly what it is.
Yeah.
And the solution is simple, but it's incredibly powerful. Tags.
Little labels that organize everything.
Yep. When you set up any runner, you give it descriptive tags, like Docker build, or Windows 10 legacy, or GPU enabled. Then, in your .gitlab-ci.iml file, your job says which tags it needs.
So it's a direct match. If my job needs tags, Linux, Docker build, only a runner that has both of those tags can pick it up.
Both of them. It has to be a perfect match. If a runner only has one, it just ignores the job. This is the contract that guarantees your code runs in the right environment every single time.
And I guess you could have runners with no tags.
You can. And they'll pick up untagged jobs, but relying on that in a professional setup is, well, it's dangerous. Your job could land on any random machine. It's how you get those "it works sometimes" bugs.
So using tags isn't just a suggestion. It's a best practice you pretty much have to follow.
100%. Which brings us kind of seamlessly into our last big concept here, executors.
Okay.
If the runner is the worker, the executor is the method the worker uses to actually run your script. It's the how.
Let's focus on the two big ones, starting with the simplest one, the shell executor.
Right. Shell is the most direct. The runner just runs your commands directly on the host machine's operating system. Bash, PowerShell, whatever. It's really fast. No overhead.
So if my job installs a bunch of Python libraries, they just stay on that server after the job is done.
And that's the massive downside. It's fast, but it is messy. It gets contaminated. If job A installs version 1 of a library and job B needs version 2,
job B could break because of what job A left behind.
You've got state leakage. And sure, you can try to write cleanup scripts, but what if the job crashes halfway through? The machine is now in a broken state.
I see. That's why the Docker Executor is basically the industry standard now.
It solves this problem so elegantly.
So how does it work?
The Docker Executor gives you perfect isolation. When a job starts, it spins up a brand new, completely clean Docker container from an image you specify, like node.18 or something. All your commands, all your tests run inside that isolated container.
So Docker's like the clean room. You go in, do your work, and when you're done, the entire room is just gone.
Exactly. The container is ephemeral. It gets deleted right after the job finishes, whether it passed or failed. Every single build starts from an identical, pristine environment. It completely kills those "it works on my machine" problems.
And I know it has some more advanced tricks up its sleeve, too.
It does. A huge one is service containers. Let's say your tests need a database, like PostgreSQL. The Docker Executor can automatically spin up a separate PostgreSQL container, link it to your main build container, and then destroy both when it's done.
So you can create a temporary, clean, full integration environment on the fly for every single commit.
Every single time. And you can use Docker volumes for things like caching dependencies, which helps you get back some of that speed you lost from not using shell. It's the best of all worlds. Speed, power, and most importantly, reproducibility.
This has been incredibly useful. Let's do a really quick review of the 5 key points we've hit, just to make sure you have this locked in.
Let's do it.
First, the architecture. The GitLab instance is the manager. It coordinates. The runner is the worker, a totally separate thing that does the actual work.
Second, communication. The runner pulls the instance. It's a pull model, which is a huge deal for security, letting runners live safely behind firewalls.
Third, configuration. Shared runners are easy and generic. Specific runners are more work but give you crucial control over your environment and can save you money.
Fourth, routing. Tags are the essential matchmaking service that ensures your jobs run on the right kind of machine. Windows jobs go to Windows runners. Simple as that.
And fifth, the method. Executors. And the Docker Executor is the gold standard. It gives you that perfect, isolated, clean room for every single build.
Nailing these 5 concepts really moves you beyond just writing YAML. It empowers you to understand and diagnose why your pipelines are really failing when they do.
So as we wrap up, let's leave you with one final thought, building on what we said about that polling security model. We established that the polling lets a specific runner deep inside a secure corporate network reach out to GitLab and pull a job in.
Correct. So the job is now running safely behind the firewall.
But think about this. Once that runner is running the job, say, compiling your code, it often needs to reach back out again, maybe to the public internet to download packages, or to an S3 bucket to store an artifact.
Right.
So the polling solves the inbound problem, but the worker's outbound needs create a whole new layer of network security challenges you have to think about.
And thinking through that whole network path from your internal runner out to public services and maybe back into other internal services, that's really the next level of CI/CD architecture. It's where the network becomes just as important as the code.
An absolutely essential thing to consider. Thank you for guiding us through the engine room today.
My pleasure.
And thank you for joining the deep dive. Now go apply this and build a better pipeline.